11:36 in the morning, August 14th, 2018. A summer storm is sweeping across the port city of Genoa. On the Polcevera viaduct, locally known as Ponte Morandi, traffic is moving in both directions. 35 vehicles are on the deck. Then, a 210-meter section of the bridge breaks free from its supports. The span falls 45 meters into the river valley below, taking those vehicles with it. The collapse is over in about 11 seconds. 43 people are killed, and 16 more are injured at the debris site. There was no seismic event that morning. There was no earthquake. There was no unusual overweight truck convoy on the deck. The forces acting on the structure at the moment of failure were completely normal. Within the envelope the bridge had carried every other day of its 51-year operating life. To see why it collapsed, we have to look at the relationship between demand and capacity. This chart shows a basic engineering principle. The smaller bar represents the everyday traffic load, or demand, placed on the bridge. The larger bar represents the total structural strength, or capacity, built into the design. For 5 decades, the internal capacity had been quietly dropping. On the morning of the collapse, that residual strength finally met the everyday demand. When the safety margin reached absolute zero, the bridge fell. The collapse was the end of a 40-year paper trail of warnings, a documented descent toward failure that was ignored until it became inevitable. Opened to traffic in 1967, the viaduct was the centerpiece of the motorway connecting Genoa to the French Riviera. This panoramic view shows the design by Riccardo Morandi, which was celebrated at the time as a modern marvel. Morandi used a cable-stayed system with a specific vulnerability. Unlike a standard multi-cable bridge that relies on dozens of stays for redundancy, this design used only 4 cables per span. If any single stay failed, the geometry of the entire deck would change in a way the structure was not prepared to handle. To protect the steel cables from the salt-laden Mediterranean air, Morandi encased each one inside a sheath of prestressed concrete. The concrete was designed as armor, isolating the high-tensile steel from moisture and chloride ions blowing in from the sea. This armor created a structural element that was impossible to inspect. It buried the cables alive. Engineers could not see the interior, could not probe it with standard tools, and could not reliably test the steel without partially destroying the concrete protection itself. During construction, the grout meant to fill the space between the steel and the concrete was not injected perfectly. Empty air pockets remained. Over time, cyclic stress from heavy trucks cracked the concrete sheaths, allowing water and salt to pool inside those voids, directly attacking the steel. The very mechanism built to protect the bridge had created a permanent blind spot. While the outside of the stays looked solid, the vital steel components were left defenseless against internal corrosion. Riccardo Morandi himself wrote the first warning. In a 1979 report, only 12 years after the bridge opened, he noted the surface concrete was already decaying. He stated that the bridge would require an invasive corrosion treatment within a few years. That treatment was never carried out at the scale he envisioned. 13 years later, in 1992, Professor Manfred Wicke was invited to inspect the viaduct. His report became the clearest single warning the bridge operators received. Wicke examined the stays on Pier 9 and Pier 11. He found missing grout, broken steel strands, and extensive corrosion. Wicke's conclusion was chilling. He stated in 1992 that the bridge was dangerously close to failing. The bridge carried traffic for another 25 years. In 2017, engineers performed a dynamic analysis, recording the way the bridge vibrated under load. The tests showed asymmetric mode shapes, a structural fingerprint of damage. One side of the bridge was carrying less weight than the other. Something inside was missing. By February of 2018, electrical tests showed an average reduction in the cross-section of the steel tendons of 10 to 20%. 1/5 of the metal holding the bridge up was gone. On August 14th, the severely weakened southeast stay on Pier 9 snapped. Without an alternate path for the load, the geometry of the span was destroyed. The deck rotated, dropped, and broke apart on the way down. The physical collapse took 11 seconds. But the forensic evidence shows it was the inevitable conclusion of a 26-year countdown meticulously documented by structural experts. Any decision to close the bridge had to account for the reality on the ground. The viaduct didn't cross an empty field. It stood directly over factories, rail lines, and residential buildings in the middle of a populated industrial valley. Operators were balancing two different timescales. There was the slow, invisible, and theoretical chemistry of internal corrosion, and the immediate, visible, and expensive reality of city economics. Closing a major artery of national infrastructure would have caused immediate disruption to heavy truck routes and the thousands of people living in the shadow of the spans. This created a loop of bureaucratic deferral. There was always a reason to wait for the next study, the next inspection, or the next contract cycle. A €20 million reinforcement contract was eventually drafted and scheduled to be signed in September of 2018, but the bridge actually fell 1 month earlier. The tragedy was a systemic failure of risk management. Operators weighed the immediate economic friction of closing a highway against a slow, certain chemical reality, and they chose to wait until the chemistry won. Following the disaster, the remaining pylons were demolished. In 2022, the criminal trial of 59 individuals, including the former chief executive of the bridge operator, opened in Genoa. The site is now occupied by the Genoa-San Giorgio Bridge, which opened in August of 2020. The Morandi case is a reminder that engineering failures are often human failures. The warnings were not missing. The willingness to act on them was. If you found this investigation useful, take a look at the other case files on the channel, like the Sampoon department store collapse. Subscribe to be notified when the next study goes up. We will see you in the next one.